vector equation of lines in 3 space. So in 2 space, we represented lines using vector equations, parametric equations, or scalar equations, or slope-y-intercept form like you're used to in grade 9. Lines in 3 space are really similar to that. The only difference is we can't do a scalar equation. So a scalar equation defines a plane, so we can't use a scalar equation in 3 space. But we can still do a vector and parametric equation. And there's something else called a symmetric equation that we're not going to worry about. But we're going to focus on vector and parametric equations of lines in 3 space. But like I said, important to know, you cannot do a scalar equation of a line in 3 space. And just like in 2 space, to write the vector equation of a line, you need a position vector to a point on the line and a direction vector that is parallel to the line. So let me show you what that looks like. So if we want the equation of this line here, this line's in 3 space, what we need to do is find a resultant vector that can point to any point on this line. And that resultant vector is a sum of 2 vectors. It's a sum of a position vector that points to a point on the line, plus a direction vector, which is parallel to the line. And if we add those 2 vectors together, what we get is a resultant vector which has its tip at a point on the line. And then how we can get that resultant vector to point to any point on the line is by varying the scalar multiple of the direction vector. So as I multiply that direction vector by different scalars, notice it makes that resultant vector point to different points on the line. So by adding the position vector and a scalar multiple of the direction vector, I get a resultant vector that points to any point on the line. So we say that that resultant vector is the vector equation of the line. So let's do just a couple examples. So this table just shows you the different ways we can write the equations. The vector equation, like I said, is a sum of the position vector plus a scalar multiple of the direction vector. And R0 is usually what we use for the position vector, and M is usually what we use for the direction vector. And each of those vectors, now that we're in 3 space, have 3 components to them. And once we have the vector equation, once we come up with this, we can easily separate it into its x, y, and z components to come up with the parametric equations. The x component of the resultant would be the x component of the direction plus a scalar multiple of the x component of the direction vector. I think I said direction twice. X component of position vector plus scalar multiple of x component of the direction vector. And that's how we get that part of the parametric equation. And same reasoning for getting the y and z components. We won't worry about the symmetric equation. We're just going to focus on vector and parametric equations. So let's do 2 examples. Example 1, let's find the equation of a line that passes through these 2 points. So if we want the equation of a line that passes through those 2 points, we're going to need to know a direction vector, a vector parallel to the line, and also a position vector, a vector that points to a point on the line. So here's what the line looks like. This is the line. We know 2 points on the line. If we want the equation of that line, we have to start by picking one of those points to get our position vector to point to. I'm going to get it to point to point A, so we'll make our position vector we call R0 is equal to the vector 2, -1, 5. And now we need a direction vector. We need a vector that's parallel to the line. So since we have 2 points on the line, we could find a vector parallel to the line by finding either vector AB or vector BA. It wouldn't matter. Both of those vectors would be parallel to the line. So I'm going to find vector BA. And let me just translate that so that its tail is at point A, so you can see what the resultant is going to be. So we'll find vector BA, and then we'll add it to the position vector. And when we do that, if I add those 2 vectors together, notice the resultant will have its tip at a point on the line, and we can vary the scalar multiple of that direction vector, and it'll bring us to any point on the line we want. So let's find our direction vector, vector BA. So direction vector, I'll make that vector BA. And to find vector BA, make sure you always do tip minus tail for the x, y, and z coordinates. So when we're doing vector BA, A is at the tip, B is at the tail. So for the x component, we'll do the x coordinate 2 minus the x coordinate 3. 2 minus 3 is negative 1. Y coordinate negative 1 minus y coordinate 6. So negative 1 minus 6 is negative 7. And z coordinates, 5 minus negative 4 is 9. Now we could use any scalar multiple of this for our direction vector. Usually we want to reduce it if possible, but this one doesn't reduce. Other than if we wanted to, we could take out a negative 1. It's equal to negative 1 times 1, 7, negative 9. Doesn't matter. We could use either version. We could use that version or that version. I'll just use the first version. So now that we have a direction vector and a position vector, the vector equation of the line would be equal to this. X, y, z equals the position vector, 2, negative 1, 5, plus a scalar multiple, I'll make that scalar t, of the direction vector, negative 1, negative 7, 9. So that's the vector equation of the line. I think part B will ask us to write the parametric equation of the line. Yep, so let me just copy and paste this over. And we'll use this to help us write the parametric equation. Any questions so far? Just throw them into the chat. No questions? Okay, so the parametric equations of the line. So we say the line, its parametric equations. I can do that better. We need an equation for the x, y, and z components. So for the x component, we do 2 minus, sorry, I thought I was going to sneeze. We have 2 minus 1 times the scalar t. So the x component is equal to this part of the position vector plus t times this part of the direction vector. So x equals 2 minus t. Y would equal to negative 1 minus 7t. And z would equal 5 plus 9t. And those are the parametric equations. So if you have the vector equation, it's easy to write the parametric equations of the line. All right. Part C wants us to check if this point 0, negative 15, 9, is on the line. So in order to check if it's on the line, we have to use the parametric equations. So let me just copy and paste this over. And we're going to check and see if that point is on the line. If this point is on the line, there should be a single value of t that I could sub into these equations that would get me to that point. So what we're going to do is we are going to separate these parametric equations, one for x, one for y, one for z, plug in the point for x, y, z, and see if we can solve for a single value of t. So we had x equals 2 minus t. We'll set x to 0 because that's the x coordinate of the point. 0 equals 2 minus t. Y was equal to negative 1 minus 7t. So negative 15 equals negative 1 minus 7t. And z equals 5 plus 9t. And the z coordinate is 9. And we'll solve all three of these equations. And we'll see what we get. So for this first one, we get t equals 2. For this next one, we'll add the 1 over. So I have negative 14 equals negative 7t. And I get t equals 2 again. But for this one, I would get 4 equals 9t. So t would equal 4 over 9. So notice the three t values are not the same. That means the point is not on the line because there's not a single t value that could get us to those x, y, and z coordinates. So we would say, therefore, point C, which was 0, negative 15, 9, is not on the line. If we had gotten the same value for all the t values, then the point would have been on the line. But since we got different values, we know it's not on the line. So let me just plot that point in GeoGebra just to show you that it's not on the line. So it was the point 0, negative 15, 9. Let me just plot that. So there's that point right there, point C. Notice it is not on the line. So there is no scalar multiple of the direction vector I could use to get me to that point. The resultant vectors are always on the line, so I can't get to point C. That's why we got different values for t. Okay, we're just about done. Let's just do one more example. Example 2, find vector, parametric, and symmetric equations. Let's not worry about finding symmetric equations. They're not very important. I'm just worried if you can come up with the vector and parametric equations of the line that passes through these 2 points. Okay, so let's look at that one. So it's passing through 2 points. Again, it's the same process. We have to come up with a position vector that points to one of the 2 points. So I'll get it to point to A. Then we'll get a direction vector by finding either vector BA or AB. Doesn't matter. So I'll do AB this time. And when we add those 2 vectors, we get a resultant that points to a point on the line. And then we multiply that direction vector by a scalar that allows the resultant to go to any point on the line. So our position vector, we call R0, has to point to a point on the line, so we'll make it the vector 2, negative 1, 3. But it could have been 5, 1, 1, doesn't matter. And the direction vector, we can make it vector AB or BA. I'll do AB this time. So when I find that vector, do tip minus tail. So the components of B minus the components of A. So 5 minus 2 is 3. Now do the y coordinates. 1 minus negative 1 is 2. And the z coordinates. 1 minus 3 is negative 2. So that's a direction vector. And the vector equation of the line, x, y, z, would equal position vector 2, negative 1, 3, plus a scalar multiple of the direction vector, 3, 2, negative 2. So that's it for the vector equation. And let's do part B where we write the scalar, or sorry, we can't write a scalar equation. Part B where we write the parametric equations. Oh, it's not separated into part A and B. It just says in this whole question, write the vector and parametric. Okay, so the parametric equations, we'll write the line is equal to the following x, y, and z equations. So the x equation just describes how we get the x component of the resultant vector. So 2 plus 3t is how we get the x component. The y component we would get by doing negative 1 plus 2t. And the z component we would get by doing 3 minus 2t. So there are the vector and parametric equations. Alright, that's pretty much it for this lesson, guys.